So today we are back in the land of probability, and we are talking about independent and dependent events. And I'm not entirely sure, this may be, you may have to skip a page in your notes packet to find this, but I can't remember if I put an extra sheet in there or not. So make sure that you are looking at independent and dependent events before we start here. So you can probably imagine where these definitions come from, but independent events are two events where the probability of one event occurring does not affect the probability of the other. And I should have mentioned this when we first started today, but all of the situations we're talking about today are and situations. And here's what I mean by that. We are looking at scenarios where we're finding the probability of this and that happening. Okay, we're looking at the probability of two things happening at the same time. And when you do that kind of probability, you have to be careful that you're not affecting the outcome of the second event with the first event. Okay, and you'll see what I mean by that in a minute. But so two independent events would be two events that are entirely unrelated. Okay, and you can find the probability of those two events. So the probability of these two events occurring is just multiplication. Okay, that's the big takeaway here, is that if I want the probability of this and that, I do the probability of the first thing times the probability of the second thing. So anytime we're talking and, or two things happening at the same time, that's going to be multiplication. Okay? I guess I could actually write out multiplication. Okay? But the thing you have to take into consideration when you look at that second event is it being affected by the first event? Okay? And you'll see, again, what I mean by that in just a minute. So, as I'm sure you would expect, dependent events are two events where the probability of one does affect the other. And feel free to abbreviate that or paraphrase it in any way that makes sense to you. One more thing that comes up with dependent events is conditional probability. And conditional probability means, what are the chances of this one thing happening if we already know this other thing has happened? Okay? The notation for that looks like this. Probability of B given A. Okay, so this is the probability that this, whatever B is, what is the probability this will happen given, that's what that line in the middle means, that A has already happened. So what's the probability that this will happen if we already know this has happened? Okay, that's called conditional probability. And the reason we have to touch on that now is when you're talking about dependent events and you've got that and situation, it's still multiplication that you're dealing with. But instead of just multiplying this probability by this probability, the second probability, you always want to calculate it on a conditional, meaning what are the chances that it will happen if we already know this one has happened? Assume that that first thing you wanted to happen did happen, and now let's multiply by the probability of the second. Okay? So I'm going to give you just a second there in case you're still writing. Okay, so right here we are just deciding whether or not these are, or whether these are independent or dependent. So if I toss one coin and then I toss the other coin, what I want to know is, are the results of the second coin toss in any way affected by the results of the first coin toss? And the answer is no, they're not affected by each other. So this would be independent. Okay, Mrs. Torigno puts each student's name on a piece of paper. I pull one name out to answer a question, then I throw it away and pull a second name out. Okay, so I want you to think about this. If I pull out a name the first time and then I throw it away, okay, and you didn't get called that first time, is the probability of your name being called the next time greater than it was the first time? Okay, is there a better chance that I'll call you the second time? And if you can't conceptualize that, think about if I did that 10 or 15 times in a row. each time that I do that, the chances that the remaining people get called is going to get bigger, okay? Because there's fewer to choose from. Every time I throw one away, and that's called being without replacement. You're going to hear that a lot. If you do something without replacement, meaning you take something out and you don't put it back, that's automatically a dependent situation, okay? Because the probability of the second draw changes based on what happened the first time, okay? If I pulled so-and-so's name the first time, I'm not going to pull their name the second time, okay, because I threw it away, and there's fewer names in the draw, okay, or there's fewer names in the bucket to draw from, so the probability changes based on the first event, okay? Now, if I took that sheet of paper with the person's name on it out, they answered question 1, and then I threw it back in the bin where I was drawing from, then nothing would have changed for that second time, okay, for that second draw. Nothing would be any different. It would be the exact same probability the second time as it was the first time, and that would be independent. That would be called with replacement. But without replacement, automatically dependent. Okay, Wednesday's lottery numbers and Saturday's lottery numbers. So a lottery is just a random drawing of numbers, okay? Random drawing of numbers on Wednesday, random drawing of numbers on Saturday. Unless I kept those numbers out, unless I drew the numbers on Wednesday and then kept them out of Saturday's drawing, which that's not how a lottery actually works. But if that were the case, this would be a dependent situation. However, a normal lottery, this would just be independent. Okay, because Saturday's drawing is not based at all on what Wednesday's drawing was. The numbers might be the same, they might not. There's no impact there. Okay. Katie and her friends going to a concert. We draw slips of paper to determine who will ride in a car and who will ride in a van, because I'm sure that's how you and all your friends decide who's riding with who. We've got 5 spots in the van and 3 spots in the car. Katie draws a slip. Not liking the outcome, she puts it back, and that's important, and draws a second time. What is the probability that both of her slips put her in the car? So what we are really looking for here is, what is the probability of her getting car and car again? Okay? Well, because she put it back, these are independent events, all right? Because the probability for that second draw is exactly the same as it was the first time. So the probability of getting a car spot would be 3, because there are 3 spots in the car, out of 8, because there are 8 spots altogether. So 3 out of 8 times, now because I took that car slip out and put it back in the draw, I still have 3 car slips, and I still have 8 slips altogether. Okay, so probability is the same for the first and the second. That makes it independent, and this would work out to be 9 out of 64, or I don't have a calculator in front of me, but or whatever that decimal is. Okay, if you wanted to figure out the decimal, you could. It's going to be about 1/8. It's going to be about 0.125, but not exactly. Now let's look at this. This time, so exact same scenario. This time Katie draws a slip and doesn't put it back. So this time, what is the probability both her slips put her in the van? So I want the probability of van and van. Well, probability of getting van the first time would be 5 out of the 8. But this time she draws that van slip. She doesn't put it back. She throws it away and she reaches in and grabs another one. So there are no longer 5 van slips of paper. There are now 4 because she threw one away. And there's no longer 8 to choose from. There's 7. Okay, so these are not independent events because the probability did not stay consistent from one draw to the other. Okay, multiply straight across still, and I get 20 out of 56. And again, if you wanted to figure out that decimal, you could. It's going to be a little less than 1/3, but again, you could calculate that if you want to. Or I guess we could reduce this. It would be, let's see, if we divided by 4, it would be 5 out of 14. okay, which again is a little less than 1/3. So, or I'm sorry, a little more than 1/3. Okay. This problem is actually a conditional probability problem. So there's no multiplication here. It's just conditional. And I'll show you what I mean by that in just a minute. So we've got 8 students drawing cards 1 through 8. Odd numbers get to be on the proposition team. Even numbers get to be on the opposition team for a debate. And it says if Jose is on the opposition team, what is the probability he drew the number 2? Okay, I want you to think about something for a second. So here's our 8 cards. I want you to pretend that it didn't say this. Okay? If I just said, what is the probability he drew the number 2, that would be 1 out of 8, right? Because there were 8 cards to choose from. So that'd be a really simple probability, 1 out of 8. But the fact that it says, we know he is on the opposition team. So here's our conditional. Here's where the conditional comes in. We already know that he is on the opposition team. And if he's on the opposition team, he must have had an even number. So that automatically, we assume that that piece of it already happened, which means that he couldn't have any of these odd numbers. Now I only have 4 choices left instead of 8. So instead of a probability of 1 out of 8, the probability actually becomes 1 out of 4. Because we know he had to have 2, 4, 6, or 8 to be on that opposition team. So that's what I meant earlier when I said the probability of B given A. What's the probability that he drew the number 2 given that he was on the opposition team? Okay, so it's not just the probability that he drew the number 2, it's the probability he drew a 2 when we already know something else is true. Okay, this one's a little bit strange. Let's suppose I know 52% of students own an iPod and 38% of students own an iPod and a smartphone. And I want to know what's the probability that a student owns a smartphone if he or she also owns an iPod. So this question is a conditional probability. It's saying under the condition that we know they own an iPod, what are the chances that they own a smartphone as well? Okay, but this one's a little bit weird to think about. So I'm going to write down the formula from a couple of slides ago. It said that the probability of 2 things happening when they're not independent. So the probability of iPod and smartphone, okay, is equal to the probability of the first thing, which is the iPod, times the probability of a smartphone given that they already have an iPod, okay? So that's what we said before, is we said that the probability of 2 things happening when they're dependent, okay, and that's what's happening here, is if we have a percentage of, this given this, that's a dependent situation. It's going to be the probability that the first thing happens multiplied by the probability that the second thing happens if you already know the first thing is true. So watch what's going to happen here. Okay, 52% of students own an iPod. And by the way, I'm going to make these all into decimals. So that's my probability of the iPad is 0.52. I'm sorry, iPod. 38% own an iPod and a smartphone. And look at that word right there, and. Okay, that's this, 0.38. 0.38 have an iPod and a smartphone. And what I want to know is this right here. I want to know what is the probability they have a smartphone if we know they have an iPod. So I'm going to make this like my x, okay? And then I just want to solve for x. So from there, I'm just going to take and divide by 0.52. Divide this by 0.52. And I'm going to get that the probability is equal to 0.73. So this one was asking you to find a conditional probability, and it gave you the probability of both of the things being true and the probability of one of them being true. So given that we know one of them is true, what's the probability that the other is true? Okay, and that probability would be 73%. So if I pick one of these students, if I say I'm only going to pick from those students, there's a 73% chance that this person will also have a smartphone. Okay? Okay, homework is just some examples that are very similar to these ones I've given you here in your notes. You should be able to get it done no problem, and we will go over it in class tomorrow. Second hour, remember, I will not see you tomorrow. You've got that big, long 3-hour block with your first hour teacher tomorrow, but I will see you on Wednesday. Sixth hour, your assignment is due tomorrow.